in machine learning, one can make a distinction between what's called generative approaches versus discriminative approaches. And to talk about these, let's think about a classification setting. So say we've got data points in R2. So we've got R2. Our x's are in R2. Maybe that's one axis, so that's like the x1, that's like the x2. And we've got some points. Maybe I'll draw them as red for one class. Something like this. One class. And maybe I'll do blue. Another class, something like this. So we got these points. Maybe this is a little sparser over here. Got some points here, and there's not a clear, they kind of overlap here. So now if we had a new point, right, classification, you would say, so maybe an easy one would be like over here. So what's that? Well, looks like it ought to be a blue. And in a generative approach, so we'll talk about, actually let's talk about discriminative first. So discriminative approach, you model, so let's say that x is, so we get this data x1, y1, let me use superscripts here, x1, y1, first data point labeled, and then we get some more data points up to, say, n, xn, yn. And a discriminative approach would be to model the probability of the y's of a y given its x. So I'm taking x and y as a prototypical point here. So x and y, or maybe you could think about x and y as a new point that we need to classify. And we're going to model in a discriminative approach. So let me say this is discriminative. We're going to model the probability of y given x. So given this new x here has some coordinate x1 and x2, and we want to predict its class. So if we had a model, so say we had a simple model where we only paid attention to, in this case, it looks like x2 isn't doing very much. So maybe our discriminative model only pays attention to, say, x1, and we say that the probability of y given, say, this is the first coordinate, x1, maybe it only depends on that. Or let's make it clear. Let's just keep it as x, and then there might be an x2 axis, but maybe the probability is doesn't well, it can't be constant, but it would be oh yeah, I guess it could be constant. It could be constant in the x2 direction. So the probability of y given x is say it looks something like this. So if we call these reds, call that 1, class 1, and we'll call the blues class 2, or rather 0. Then the probability that y equals 1, so let's say that. So let's say probability that y equals 1 given x, say this is 1. So maybe when it's over, when we're in here, we're quite certain. So this is going to be close to 1. And then it drops off very quickly. And then when we're over here, we say, for these x1 values, we're pretty sure that the class is 0. So the probability that y is 1 is very small. So maybe we have a discriminative model like this. Now, a generative model, on the other hand, would model both. It would model the joint distribution, x and y. So in this case, the x's might have some, so we could factor this as the density, let's write it as f. So the density of x given y times the probability of y. And these densities, so for example here, we might have a density for the 0 class that looks something like, well, maybe a Gaussian, something like this, right? That might be Gaussian for that guy, and maybe a density for this guy that's sort of concentrates in this region. And in a generative model, since we're paying attention to the distribution on x, so we could also, instead, we could write this as the probability of y given x times the marginal density of x. And in a generative model, you model the densities as well as, so you could view it two ways. You could view it as the class marginal probabilities and then the conditional density of x given the class, or you could view it as just some marginal density on x and then the probability of the class given the x. So the discriminative part shows up here. And in this example, which I chose to illustrate this, suppose we now had a point over here. Suppose you were asked, you were given a new x over here, and you wanted to predict its value, its class, its y. Well, in this discriminative type of model, you would probably say that that's class 1. But in a generative model, if you were modeling these class conditional densities, then you would probably be more inclined to say that that belongs to class 0. So in this perhaps contrived example, at least, and more generally, I mean, a generative model is more powerful in some sense than a discriminative model because, well, you're just accounting for more things. But there are good reasons to use discriminative models, some very good reasons actually. It's not just the fact that you're being lazy and sort of ignoring this other part. It's so the reasons. Well, one reason is that in a generative model, you have to estimate these densities. Well, one of these at least. If you take this approach, you have to model these, and estimating a density takes a lot of data, and statistically speaking, it's very difficult to do. So you're inclined to make mistakes. Your estimates will have high variance, especially if you don't have much data. That was a sort of statistical argument there, but generally, and you can probably see that it's going to be difficult to model this density unless you have lots of data. And as a result, a generative model can have worse performance than a discriminative model. So that's what people mean when they talk about generative versus discriminative models. And let me explain this terminology, why these are called generative at least. So generative models, well, often they have a very natural, so one sort of appealing thing about generative models is that they also often have a very natural sort of interpretation, and it's in terms of a generative process. So this formula suggests it here. So the generative process, which we might describe this data by, would be, first we're going to choose a class y, 0 or 1, in this case just 0 or 1 since these are our only two classes. So we choose y according to its marginal distribution. And then given the class, we're going to choose a point. So first we choose 0, maybe, and then we pick some point. That's what's called the generative process. And then maybe if we run the generative process again, maybe we pick 1 this time, and then we choose I don't know, say this point. We choose it from the margin from the conditional distribution on x given y equals 1. So that's why it's called a generative process. Versus a discriminative. In a discriminative, you don't have any distribution over the x's, so you can't generate the x's. All you can do is sort of discriminate between the classes given x.